I see the primary answer that a lot of y'all put was 2x squared minus 28. Does one of these lovely people want to explain what's going on? Why 2x squared minus 28?
When you write out the equation, between both parentheses is multiplication.
It is multiplication, that's right.
So
Put a little multiplication symbol there.
all you gotta do is write a one. Write one at the front right there.
One right here? Okay.
But
What's that
no,
doing
cause that'd
for
be
us?
wrong.
I mean, we can always multiply by 1. That's never wrong.
Okay. But then when you, well no, okay, yeah I did it right. So you do 1x.
Okay.
Then
You want me to write it down here?
Yeah. Then you will do minus 4. You will do minus 4.
So I'm taking it out of the parentheses now?
Yeah.
Okay. What's happening with this other parentheses? The other group of...
I really didn't really think that one through. I just took it out of parentheses. I really don't have a reason to take it out.
Does anybody else that put 2x squared minus 28 want to explain their reasoning? You got it. What you thinking? So you said 7 times 4 is 28? Or negative 4 times 7 would be negative 28? Does anybody have anything to add to, so I guess the basic concept, Jacoby, you were explaining this to me. Well, explain what you did for this.
I timed it together, like I did it come by times.
So you said this term and this term are similar, and so we can multiply those together and we get what?
2x squared.
And then you said this term and this term are similar, so we can multiply those two together? So that's how Jacoby got that. Does anybody have any pushback? Anything they want to add to that? Do we think Jacoby's right?
You gotta be in standard form.
Hmm?
You gotta be in standard form.
Is this in standard form? How come?
There's no B. Oh, there's no B.
Could I not rewrite it as,
Oh,
my b is just 0?
no, you right.
Okay, so it's in standard form. What Jacoby said is in standard form. Does anybody have any issues? David, you were raising your hand earlier. Was this, you're good? Okay.
I put multiply everything in between parentheses and that.
Okay, so what did you put for this?
I did 4 times 2x and then 4 times 7, negative 4.
All right, let's work through that. X minus 4, 2x plus 7. So you did,
X times 2x and x times 7.
okay, so x times 2x. Let's think about this though, right? Jacoby was making an interesting connection, right? If this were addition, this would be the correct sort of procedure to say, like, what are my like terms? And let's work with those, let's combine those like terms. We've heard that sort of terminology before. But I think the reason Mr. Kenny doesn't like the terminology combined like terms is because that can get tricky with different operations. Because we can only add x and 2x together, we can't add x and 7 and combine that into one term. But we can multiply x times 7, right? There's no issue with multiplying that. So carry on, Tyson. So you said x times 2x, which is
2x squared.
2x squared.
Can you do this, because I think this will help some
Yeah.
students visualize it. Can you write just that x times 2x?
Yeah, sure.
Does that make sense?
Yeah.
And then we'll simplify in a second.
Yeah.
But
Okay, so that's one term. And then what'd you do after that?
X times 7.
So x times 7. So we're multiplying this term by this term, and then we're multiplying this term by that term. So plus x times 7. And then what?
And then 4 times 2x.
4 times 2x?
Negative 4 times
Negative 4 times 2x. So I will put a plus negative 4, just so we can see it, and then we'll simplify it in a second. Times 2x. And then what else?
4 times 7. Negative 4 times 7.
Yeah. Negative 4 times 7. And then let's simplify this. Does anybody want to help me simplify this?
2x squared plus 7x minus 8x minus 28.
Minus 8x. And then, Jacoby, you can combine like terms here. What would our final expression be? What's 7x minus 8x? 1x minus 28. Apologies for the diagonal writing here, but,
We'll just have to work on that.
yeah. So, I did not see anybody using what I'm about to teach you guys, but this, let me finish with the arrows. You guys may have heard of foiling before, but that only works with binomials, and it's also a little bit of a shortcut. It's a method for multiplying binomials, and you end up with this. But I'm going to teach you guys a different way to multiply that will work for any set of polynomials, right? So this is technically a polynomial. It's just a polynomial. What's the degree of this polynomial?
1.
And then what's the degree of this polynomial? Yeah, they're both lines. So this is just multiplying two lines together. But I'm going to teach you guys a method that you can use with any two polynomials that you multiply together. So I will do a little bit of direct instruction. You can open, actually I'll teach you first and then we're going to be in M1-176, but let's do a little bit of just direct instruction first. So let's work through this x minus 4, 2x plus 7 again. But I'm going to do something a little bit fun. You guys ready for fun? Yeah? I'm ready for fun. Doesn't matter if you're ready or not, we're going to have fun either way. So, let's think about, y'all were working on the planner boxes on Friday. Y'all remember that? So planner boxes. Yeah. Okay.
Just because there's a couple things I forgot.
Yeah.
I was meant to do during the.
What was the page number?
176, M1-176. We're not going to be working that just yet, but that's where we're going to be headed. So you can go ahead and open it up if you want to.
Really quickly, pass out beta club thing. If you do, what's it called when you work instead of co-op? Thank you. If you have co-op, I have some hour stuff for you. Where's Treyana?
Like, if you do it this year.
If you're doing it this year already, you have to have a certain number of hours. So this from Miss Jemison. Is Rakai not here either? Okay. And then I have progress reports for those who didn't pick them up, and I'll just pass those out while Mr. Kilpatrick gets going. But just a heads up, Literacy for All, I meant to get that done this weekend. It did not happen. I don't know if I've mentioned this, but my wife broke a bone in her hand, so I've been having to do a whole lot more at the house. Just taking up a lot of time, having to do all the cooking, cleaning, everything. So I'm gonna try to get those done ASAP. But why are we here?
To grow,
To grow, to learn.
to show that we're capable of it.
You don't have to prove to me you're capable. I know you're capable, right? To grow in that capability, to meet that capability. And as Mr. Kilpatrick said, let's have some fun with math as well. But don't forget, this is good and this is useful. It is a good thing when we're challenged, but let's make sure we're putting in the time and effort and make sure we're doing our best to grow and learn. And so we're on page 176. Do you want me to put that slide up?
Not yet.
Okay. So there's on page 176.
So, y'all were working with the planner boxes on Friday, which was a three-dimensional shape. It was a rectangular prism. How did we find the volume of that planner box? What was the
Lift times height.
length times width times height? Well, here we're just going to be working with a two-dimensional shape, rectangles. How do you find the area of a rectangle? Length times width. Now, what's fun about this rectangle is that each side of the rectangle is going to be one of our little terms here. So I'm going to have a rectangle with x minus 4 on one side and 2x plus 7 on another side. Now this is weird, right? Because x isn't a number per se, it's a variable, so it could mean anything. But either way, we're going to use, this is called an area model for multiplication, and it's helpful to visualize maybe what Tyson was explaining to us earlier. And so, is this looking, do we have any, you know how to do this? You seen this before? You're following what's happening here? No? Alright, let's think about it, right? So I just broke this rectangle into 4 little rectangles, right? Are we following on that? And because there's 2 terms up here, and so there's 2 terms over here, so we have a 2 by 2 rectangle. You following? Okay. So this little top left rectangle up here, what's the, we'll call this the length, and we'll call this the width. What is the length of this top left rectangle? Well, what's just the length? Just think about just the length, not the, well, yeah, the length of the whole rectangle is x minus 4. But if we break it up, right, if this is the, yeah, maybe that's, yeah, it's just x. The length of this rectangle would be -4, which doesn't make sense because this one can't be negative, but we're just using this as a model. So the length is x, and the width is what? What's the width of this rectangle? 2x, okay? So what's the area of this little rectangle then? What's length times width? 2x times x, which is 2x squared. Okay, this looks familiar. Now, which rectangle do we want to do next? Which one do you want to do next, Zeke? You want to do this one next? You want to do this one next? You want to do this one? Alright, so Marcus, let's do this one. What's the length of this rectangle right here? This little, and then what's the width? 2. And so what's the area of that little rectangle? Length times width.
So I do -4 times 2.
Times whatever the width is. Yeah.
We don't need secret. I mean, I don't know. I don't know what it is.
Yeah, you do. -4 times 2x?
Maybe secret or negative. I don't know. Dude.
What's -4 times 2?
I don't know. I ain't good at negatives.
-8. -8. So what's -4 times 2x then? -8x.
Really quick, let's pause.
Yeah.
Jim Marcus, we talked about this last week. If we have 1 negative being multiplied, is that number going to be positive or negative?
Negative.
Okay, if it's 2 negatives, it's going to be,
Positive.
and 3 negatives,
Positive. Negative, I bet.
4 negatives.
Negative. Positive.
Remember, guys, if it's an even number of negatives being multiplied, it comes out to be what? Positive. If it's an odd number of negatives, it comes out to be negative. And guys, if you don't know, what resource do every single one of us have in our hands?
Calculator.
Oh, right, guys, come on, use your resources. You can do -4 times 2 in that calculator. Use your resources.
Going back about the calculator.
Alright, Trayana, let's do this little rectangle right here. What's the length of that rectangle? Yeah, you do. Come on, up here. We got it. Monday morning. It's a good time. Good time to be alive. What's the length of this rectangle? This is the whole length up top, but we're just looking at this little piece. Just x, and then what's the width? Just 7. All right. What's the area of that little rectangle? 7x. See, this ain't too hard. You know how to do this. Who wants to finish it off with that bottom right? -28, right? We're following. Now, if this is the area, if it's 2x squared, this piece is 2x squared, this piece is -8x, this piece is 7x, this piece is -28, and I want to know the area of the whole rectangle, what would I do? Add them up. It's easy. So I have 2x squared minus 8x plus 7x minus 28. And then we simplify that by adding those two like terms together. Right? They got the same thing that we got before, but as we get to higher degree polynomials that we're multiplying together, we can just expand this rectangle, add more rows, add more columns, and it's going to be easier to multiply those together. So, look on 176.
Let's get it.
Yeah.
We got some books.
You know, I have volume 1 with you.
I do.
What's wrong?
It's weird.
Just Open up to the page, it'll dry out eventually, don't put it in your backpack if you want to leave it in here overnight so that it has time to dry, let's go with that.
So notice what's happening, they already worked out the example for you to help you see what's happening. Notice what's happening on page 176. They're asking you to determine the product of three linear factors. This looks similar to stuff we've seen before, right? Working with three lines, and what degree polynomial would this be when we multiply it out? Third degree polynomial, right? So we've been working with third degree.
Didn't you say that you wanted to talk about looking at using a calculator to check?
Oh yeah, no, that's a good idea.
I just thought that's where you said you wanted to do that.
That's true.
Okay.
Here, if y'all look in your Inspire files that the bell ringer was in.
Oh, we just sent out a bell ring, we didn't send out the file.
Oh, okay.
I'll send out the file now.
Well, the whole file. Oh, okay. you just-
But if you're doing a quick poll like this, so if you don't do a quick poll, you have to have everybody's responses back for the entire file. That's why I sent out as a quick poll, but I can send out the document now. So in the future, you just hit this little button from here, and then that'll allow you to send it to everybody. Alright, so y'all should get a file to your calculators now. Open that up. Sorry, I just thought, that is where you said you wanted to do that, right? Okay.
Yeah.
Okay.
And so, as it says in the bell ringer, which I forgot to do, let's try verifying our solution. Does anybody have any ideas about how we can use this little graph on page 1.2 to verify our solution? Because what are we trying to do here, right? This expression and this expression are what? What's the fun word Mr. Kenny always likes using? When they're equivalent expressions. And so, how can we use the graphing technology to check if they're equivalent expressions or not? Yeah, you can graph both equations, and if you see two different lines, you know you got it wrong. But if you see one line covering up the other line, then you know you got it correct. So let's try plugging in this expression. I'll show you how to do it for this one, and then we'll get some more practice doing it for the rest of class with other ones that we're going to practice. Okay, so there's f1 of x. Then let's try, we got 2x squared minus x minus 28. So do those expressions look equivalent on the graph? Yeah? So that's all that is, but we can use this as a helpful tool. If you're on a test and you're like, man, I expanded this, but I want to check to make sure it's right, you can plug it into a graphic calculator, I don't know, depending on what you would have available to you.
This test will definitely have non-calculator and calculator portions, because there will be a part where you have to sketch the graph, like we've been doing, and if I just give you a graph and calculator, I'm not actually seeing if you understand that or not. But on the multiplying polynomials part, like this, you will have a calculator.
Sure you are.
Okay, so we're gonna get some more practice doing stuff like this for the rest of class. Now, if you go back to your textbook, looking at 176. So what it's asking you to do here, we were talking about this, right? This would multiply out to be a cubic, but I don't know how to distribute, because there's three expressions being multiplied together here. That's complicated. And so what the book does, which is what we're going to be doing today, is it says, okay, let's just focus on these two terms right here. X plus, these two little expressions, x plus 2 and 3x minus 2. Let's not worry about x plus 4 right now. We'll multiply by that later. And so they use an area model to find out what x plus 2 times 3x minus 2 is. And they get 3x squared plus 4x minus 4. And then look at what they do in step 2. Does anybody observe what's going on in step 2? Yeah, we're multiplying, but what are we multiplying by? Yeah, we're taking the last binomial and we're multiplying it by this product that we just got from this area model down here. So, we're following with what's going on with this little piece? Okay. So, let's get some practice on our vertical surfaces. Is anybody still writing this down? I can erase this up here. We're good? Yes, we. So, in your groups, we will get some practice with using area models and then checking. So let's work with these problems on our vertical surfaces. Ready? Let's go. Vertical surfaces, let's do it.
Let's turn that TV on. Huh? Well, I might write out the whole expression first, and then I would start writing out the box. Okay, so I would write out my full expression first. It's gonna, remember, you want to go methodically, step by step.
I hope you watch that and be like, I'll just write you up.
And I'll say, hey, first, we're working on just the area model right now. Let's work on expanding it first, and then try. Yeah, that's a good idea. Work on, just to get some practice with the more simple examples first. Try working on B, because that's easier than A, and then we'll get to A eventually, but let's work on B first, and then. That's a good mentality, but let's test out the training wheels first, and then if you're such a savant with the training wheels, we'll let you go with the bike, you know? So.
Mapping to each other. Something to think about for the next I just first understand why
Sure.
there's three, something like that, right?
Yeah.
You can't do all it's like going to box 10 times. Does that make sense? And you can still and that's connecting to like the both things like that.
So it's these two right now.
But you can just like be injured and falling on the
Correct. Exactly, yeah, they're equivalent. The other thing is, I will point out the boat.
You're not using that same method
Do the whole box with that multiplication.
What method are you talking about from last time? Like,
oh, let me talk about like double root stuff. This ain't like that.
no. This is,
I don't think so. They weren't in the stack.
So basically he just.
That may mean you've already done it.
yeah,
I mean, he
so,
did like 8 times 5, 8 times 5.
correct. Yeah.
But they're not in this pile. No, just the first two workspaces. There's just the first workspace, which is only two.
You can, and that will get you the same thing, but we're trying to, especially as we work with these higher degree polynomials and stuff, we're trying to get practice using the area model. Practice using that, you know how to do that, so that's good. That's a good tool to have in the toolkit, but it's nice to have 2 different ways to do it. That's nice, right? Yeah, so, you absolutely could, and you would get the right answer, but that's what we want to try to practice with this.
They're right, like,
It's not too difficult an example, whichever. One thing that's just a simple error.
Oh, well then you're right then.
Yeah.
If it's not, if it's not negative, then you're right. Yeah.
Y'all can get practice working with A now too.
Every
This-
term is being added.
B, yeah, if you feel good about your answer, well, that's gonna be a positive 2 now.
All this.
And a positive 10 there.
5x plus 10x plus 10x.
So, but yeah, y'all can start working on A now.
Yes.
No, yeah, all we're trying to do is take this form and put it in. So yeah, that's all we're trying to do.
Well, notice that was where we'll find it.
Yeah, but now we're working on A, because B was just to get that right.
How many factors do we have? Now, we'll point out we have 3 terms that you can add together. So we want to do that.
like.
Mr. Kilpatrick, did you want them to go ahead and do the graph now as well?
You just like sketching it
Yeah, so sketching the graph, based on the factors.
with just the
Wait,
details.
hold on, this is, hold on.
I didn't know if that was a good plan right here, but I knew that we're supposed to be checking, and I assumed you wanted us to.
Yeah, no, that's a good point. Hey, I know B was a pretty simple example, but as always, we can plug it into our calculator. So I have a bunch of pages created for you, 2.1, 2.2, 2.3, all of those are for these 4 examples that we're gonna do. And so check your expressions to make sure that they're equivalent using the graphing technology in your calculator. And then, so in terms of sketching it,
So just
they have the
sketch
space
here,
on their template.
yeah, sketch there, and then graph the standard form to check to see if they're sketched.
So should I have them for like A, I can have them sketch it by hand, so not, or like, because it feels like those could sort of start interfering with one another if they check their answer and then they try to sketch, or if they.
I would sketch
first.
first
Yeah.
and then check.
Yeah.
Yep, that's what I would think through.
Like 3.
So now I'll try to graph this function over there.
I hit 3 rows.
It's supposed to look like that.
Does that make sense?
Hey, also.
Okay, so at this point, y'all have a standard form. Now, I will point something out. I see a positive 2 there. How did y'all get a -2?
You don't have the right.
You have put a minus right there in the first row.
There's these little graphs over here.
Right there.
It's on your last week. So,
That one.
you can practice sketching
But like right-
polynomials.
It's the
In the equation,
That's
we
too
have
hard.
number
You
2,
know how
but
to
we
do
just changed it.
I think you do know how to do it.
Oh, you've got to change the end?
Yes.
I got you. So we now know.
Okay, let's,
So I want to point this out, like we're trying to now graph this expression. How would we do that?
just explain it.
Sorry, by hand here first. We'll check our answer on the calculator. But how could I sketch what this function looks like on that graph?
Yeah. First of all, this is my inbox.
How could you sketch this function on this by hand?
But not big though.
If you have the vertex, do we have the vertex right now?
So,
No,
Say again. Well, we know that there's 2 roots, but when I look at this function right here, do you know exactly what this function would look like? Have we ever graphed off a standard form? No. But what would you use to sketch out what this standard form would look like? Say again?
so I would put this down in standard form.
So, well, how would we find our x-intercepts from this standard form? Or not necessarily from the standard form, how would I find my x-intercepts for this function?
That standard form.
Remember, we can't forget what we've been
Standard
doing.
form times
How
that.
you do this?
Haven't we been graphing off of this factor form? By graphing the first factor and then graphing the second factor and then multiplying positives and negatives? Let's try that, right? Let's sketch out what this would look like on the graph.
So,
The first one. Nice, you got
Yeah. So like I can't really graph easily off of this
so
standard
you
form.
can combine.
But can I graph y equals x plus 2?
You can, yeah.
Can I
So
graph
you can choose
y equals
whichever
5x
two you
plus
want.
1?
And you multiply
And so if I can
it. So like you
graph
have over here,
those,
right, you have 3 terms.
we've been using that to be able to sketch out what the graph looks like.
And work on that. Let's try it out.
So y'all doing.
Wait, did y'all already do the graphing
And
portion?
then they multiply that times the other term.
You gotta put it on
Right, you just go part of multiplication.
So like, right here. Okay.
Connection. You're not seeing it very good. Oh, yeah.
So how would I sketch out what
Simple.
this function looks like if I don't have the calculator?
Then I can do 10 times 33. So similarly, right, we're taking 2 of them and multiplying together.
Look at lesson 2. What do we do?
We can multiply 3 things together, like just all the ones in our head.
Did y'all take the time to sketch out the graph? Yes. So
Yeah, you can multiply
do
these
that
2
first
together.
before
and then
sketching?
later.
So I think you're supposed to now sketch what this function would look like. So you have, by the way, where's your standard? Okay, so you have this function right here, right, this expression. Now, let's sketch out what that would look like here in the book. So how would we figure out what that graph would look like?
I put a tie-dye shirt in my backpack with some saran wrap that is gonna hold.
It did not hold.
But what you,
That's
like,
okay.
what's the length?
We don't wanna lose our notes from the previous stuff. Look, see if there's a volume 1 book in there.
In the box.
In that box, yeah.
We
Think
keep
about
these
the
books
last
at
one.
the end of your
Last one, wait for it.
Okay, before that, I
No.
need to
If
that.
I ask
You don't live it.
what's 2 times
If
5
it's-
times
Just kept it.
Oh, no, it's tiny. It's like, it's a lot.
I can open the pack or you don't want to?
by the third one.
This thing.
Yeah. Put it together with that.
Y'all have multiple of that, so you got 5, 6, 3,
Put like that.
Curves here.
11,
All three of them together.
plus 2.
What do I do?
How am I gonna see that now?
Are you trying to do each of them individually as long as
Yeah, like how would I grab that?
the dilation?
I gotta grab different.
But you remember back when you find the zeros?
We don't need to solve anything. How do we sketch out what x times f of x is?
7 equal to 0? Yes.
Sketch out the
And
factors.
look equal
It's
to 0, and then
really
you can find the
similar
zeros.
to right over here.
So like when I'm
And
here,
then, well, you can also break it down what you.
I can't really do all the standard forms when I sketch out these factors.
Figure out the
So
shape.
sketch out your factors.
On this.
Graph what those factors would look like to see what your function is
Look
look
like
like.
a flat line to it.
So we know that this is zero. And,
Yeah, once you guys are also,
yeah, and negative 1/5.
sketching as well.
So-
Once you finish with these, you have a little space over here on the graphs.
Yeah,
Yeah,
so
to
you want one.
sketch based on
So
your.
then you try to
Hey guys, really quick question. Did y'all take the time to sketch out what this function is like? So we have it on the calculator, but remember, right, we also want to be able to sketch that by hand without looking.
What axis do they need to
So like, how can I sketch this out by hand without looking at that calculator?
I'll just say it's on the left side.
Yeah.
Okay, so, and I'm glad you're talking about that. So are you looking at that factor form or that standard form?
So now,
I'm always gonna solve that.
Well, what's negative?
Let's sketch out that factored form, right? And from that factored form,
yes, now
let's
we're
use
gonna
that, or those, by sketching each of those factors.
What?
Yeah, negative 6 times.
Let's try to figure out what this graph would look like and check it. Right? So let's do that, let's graph those factors.
It's not just negative 6x though, right?
What?
This is
Figure out, do it out.
negative.
Hey, no, you should.
Negative 6x.
Is this yours?
Multiply by the-
How'd you get that?
That's what happens.
No.
We have, if I give you negative 6.
Not just using a calculator, guys. Look, look. So you already have what's 5x squared plus 11x plus 2. And you want to show that work in a second. But how have we been graphing these functions? By looking at the factors. So what do I know for y equals x plus 2? Okay, the root is negative 2. Now you want to show that work. What else do you know about that function?
Oh.
This function. So we need more than 1 point, don't we?
X squared. That's why.
Come on, guys. Eyes and ears here. If I'm trying to sketch this, I need to graph this first linear
You can
factor.
put in your, oh, right.
Yeah, we're
You got
done
your zero.
sketching
You
now.
said that negative 2 was the 0, right? Because that came from 0 equals x plus 2. Okay,
So those are your two
what else do we
zeros.
know?
And then you can also put those 2 lines on there to see, is it gonna be?
Okay, the
concave
y
up or is it gonna be
intercept is
concave down?
2. And also, guys, it's a line, right? So what's my slope, right? 1. See how that's a slope of 1? Okay.
Yeah, we need, you'll do need to be able to, like, you can check on the calculator, but we should sketch beforehand because we're gonna have situations on tests where it's gonna be a non-calculated portion of the test, you gotta be able to sketch it out. And also just because it's a helpful skill to understand why the function is
There's none at
shaped the
the
way it
front,
is.
then no. Alright, those are, you need to quit, get back to lunch. Hold on 1 second, let me get these passed out. Hey guys, have we tried sketching our functions by hand yet? So we need to start there.
Well, no, so, yeah, that's the,
Okay.
with standard form, it would never ask you to graph a function in standard form. by hand.
Yeah, no, definitely not.
That's why we have the factor. So, do you remember last week?
Jose, Mr. Kilpatrick's talking.
Doing a little bit of just going over some review. Some stuff that's important that if we don't get this stuff right, then it's gonna be easy to mess up on these examples. So if I have can I add those two together? Why can I add them together? What do we mean by like terms? They got the same exponent.
Yeah.
Now let's think about why we can do that, right? And I'll just make this 4x, because it'll be easier to represent. So 4x squared, and I'll use different colors. 4x squared will be in red. We have x squared plus x squared plus x squared plus x squared. What is multiplication? Do you remember? Repeated addition. Mr. Kenny has taught y'all well. I want y'all to know, not every 11th grade classroom, if I were to walk in there and be like, hey, what is multiplication? They wouldn't be able to tell me that, so Mr. Kenny has taught y'all well. And then we'll do the same thing for 7x squared. I did too many. We'll just make this 3 or something. And so we can add these all together because they're similar, and we get what's the sum of those two? 7x squared, because you can count 1, 2, 3, 4, 5, 6, 7 x squareds. Now, if I just change that, what's happening now? If I have 4x squared plus 3x, did I do anything? Why not? Yeah. So do we have, I know it may just feel like I'm just spitting rules at you in terms of what you're allowed to do and what you can't do, but does it make sense why we can't add x squared and x together? Or why we can't combine them? We can add them, obviously, we're adding them right here. What's up? Yeah, this is an exponent of 1. Yeah, they have 2 different degrees. That's a good point to make, Jose. So we can't add them together because they have 2 different degrees. Now, I will point out, and this is maybe getting beyond the scope of the class potentially, but if I had 3x squared plus 2y squared, this is getting calculus 3 type, I don't know, maybe it's getting too complicated.
I mean, you would talk about that in pre-cal.
Yeah.
We wouldn't talk about the function, we would talk about how to evaluate.
Yeah. So, can I add these 2 together? So that's why I wanted to point this out. These 2 do have the same degree. I cannot add these 2 together. What's different about these 2? X and Y. So I can't just, how would I add these 2 together? I'd have 5 what squared? I don't know. They have 2 different variables, and so we can't, so it has to be the same variable and the same degree if we want to add them together. Is that, and that's something that, you can try to intuit, but it's also something you're just going to have to memorize as we're doing these procedures. Does it have the same variable? Does it have the same degree?
Okay, so we can add them, but we can multiply them together?
Yes. So you can't combine like terms in terms of adding. You can multiply any 2 things together. I could throw you an apple and a banana, you can multiply them together. Like, not mathematically, but like.
Yeah, how
Yeah, you can take any 2 random objects and multiply them hypothetically. But they don't have to be like terms to be multiplied together. So I wanted to go over that. I also want to maybe just as a class do a little bit of a sketching.
Yes.
It seemed like we were having some issues with sketching. Mr. Kenny, do you think it'd be worthwhile to work through expanding this, or just work on sketching it?
I think everyone, from what I saw, was okay on multiplying.
Yeah. All right, let's just work on sketching it then. Is it cool? I don't know which group this is. Is it cool if I erase the stuff that's on the graph right now? Yeah, I don't know which group this is.
The only thing I will make a note of, I think Mr. Kilpatrick talked about it, and I think y'all are starting to see it. Please note that everything inside of those boxes in the area model, those are different terms, and what are you doing with those terms? You're adding them. Please hold on to that and pay attention to that. One thing I like to do, and they don't have this in the book, I like to kind of circle my like terms with an oval. So like, if you can go over to that blue one right there, Mr. Kilpatrick, I would circle the negative 8x squared and the negative 3x squared. Like, no, just like one full,
Oh,
yeah. Those are my like terms. Those are my like terms. That helps me visually see what my like terms are to know what to add together.
Okay.
Yeah.
all right, let's work on with A, because y'all have all worked on A. Let's work on sketching A. Let's get one idea. How do we start sketching? Find the zeros. Is that what you said, Joe? Okay. So find the zeros of what?
Oh, you got another one?
Yeah, so we have all of these different linear terms that we're multiplying together. Is there any issue if I miss all of this here? Is anybody gonna have an issue with that? So, which of those linear terms do we want to work with first?
The X plus 2.
X plus 2. That's great. That's a nice easy one and it's first. Well, actually, hey, let's talk about this. This is just mathematical understanding. This is what Mr. Kenny's trying to build in y'all. So if this is our function, f of x is equal to x plus 2 times negative 3x plus 2. Someone read that last one out to me? 2x plus 1. When I'm finding, Jacoby, you were talking about finding the zeros. Why are we doing that? What's the purpose of doing that as we're sketching this function? What degree is this function going to be that we're going to end up with? Third degree? You can say it out loud. Okay. So this is going to be a third degree function. How many zeros is it going to have?
2. Oh, well, 3, but like.
Yeah, according to the fundamental theorem of algebra, what does the fundamental theorem of algebra say? Anybody remember the fundamental theorem of algebra? Something about the roots? Yeah, the roots are zeros, but whatever degree function we have, that's how many roots we're going to have. Complex roots. Some of them are going to be imaginary, some of them are going to be real. That's how many roots we're going to have. Okay, Jacoby, you were talking about finding the roots. How would we find the roots? So if I want to find the roots of this cubic function, I want to know, I'm going to have some squiggly line. This isn't going to be right. I'm going to have some squiggly line. I want to know what these 3 points are. And those 3 points are when y, or f of x, is equal to what? 0. So I set the whole thing equal to 0.
Hey guys, y'all have plenty of space in the book to write this down if you didn't already do this. I see very few pencils.
So what's happening next? Zero product property. Why can we do the zero product property? It's equal to 0 and we're multiplying 3 things together. If I had a little plus 7 over here on the end, I can no longer use the zero product property. It has to be 3 things, or it can be as many things as you want multiplying together, but it has to just be the multiplication. So if I had something else hanging out over here on the end, we can't use the zero product property, but we just have 3 things multiplying together. And so what does the zero product property say? If this, yeah, so the zero product property, the whole point is, if we're multiplying things together and the product is 0, then at least one of these things has to be equal to 0. So we set all of them equal to 0. And then we solve for the roots. That was pretty easy. Similar procedures over here. Does anybody have any, is this all pretty familiar stuff in terms of how we solve for these zeros? I'm multiplying by the reciprocal of -3. So I get x is equal to -2 over -3. Well, what can I do with that? Yeah, a negative divided by a negative is going to be a positive. I'll finish in a second with that third one, but let's go ahead with these 2 lines that we just started with. X plus 2, start right here. Let's graph this line, roughly. And does anybody have, I mean, this is, like, we've been doing graphing lines for a long time. Does anybody have any issues with what happened here? I started with the y-intercept because that's given to me. X plus 2, and I just use the slope of 1. We all good on that? The second one has the same y-intercept, positive 2, but this time it's got a slope of negative 3. So that is what that second line would look like. And as you can see, right, we said the 0 was at 2/3. And where's that 0 at? Somewhere between 0 and 1, a little bit closer to 1. It's at 2/3. Yeah, down 3 over 1, because it's a slope of negative 3. Yeah. And then for this last one, I write so diagonal.
You sure do?
2x plus 1 equals 0. We having any issues with that? This is all stuff we've done before. So I know these are my 3 zeros, and I can see that when I graph the lines. This one starts at 1, goes. And these sketches don't have to be perfect. I don't think the purpose of these sketches is for you to be perfect. It's to understand the shape of what's going on here. So, as we said, we were trying to identify these zeros. What do we do now? We have the 3 lines, and we have the 3 zeros. What do we do with this? If we're trying to sketch it.
I got a question.
You got a question?
Why
What's
you
up?
didn't start on the x-axis? Why start on the y?
So when I'm graphing these lines, the easiest place to start graphing a line would be at the y-intercept, especially if it's given to us, right? But we do have to take note of where the roots are. So I could have started graphing right here. I absolutely could have. But especially when we're given the y-intercepts, if we're just trying to graph the lines and the shape of the lines, that's the easiest place to.
Mr. Kilpatrick, is the meter stick not up there somewhere?
It is. I could use it to make it real straight.
Just in the future, yeah.
Yeah.
Guys, if you are drawing lines, get a ruler.
Yeah.
How y'all so ugly?
They are ugly lines, but that's all right. I'll use it.
I don't know that I would consider those lines, but you know.
Like,
I'm just saying, I can't draw a line without a ruler, that's for darn sure.
Oh, yeah. Yeah.
I am not an artist.
now we on,
No, what's up? What's up?
oh, I know we done.
We ain't done yet. We're trying to sketch
Yeah, we got
the dashed lines. Okay, what are we doing with those dashed lines?
put them between the zeros. I mean,
We're gonna put one
who the zero?
at each of the zeros. Jose, you start.
My bad.
Gross noise.
No, it's DeMarcus. That
That was DeMarcus?
Yeah. It's negative 1.
DeMarcus thing. Come on, man. Alright, man, those are horrible lines. Y'all get the point, alright? We're working with it.
Your line's bad, your right bad.
I didn't go to art classes. So we got these dashed lines. What are we doing with those dashed lines?
It's going to tell us how
Okay, we're gonna look, right, we've broken our graph into 4 sections here, right? We got this section over here. We'll call this section A, why not? And we got section B between these 2 zeros, we got section C between these 2 zeros, and we got section D over here. Do you see how we've broken the graph into 4 sections? Is that making sense? And the shape of this function is gonna be dependent on which section it's in. So for this section A, what's the function? Is it going to be positive or negative? Why is it going to be positive? So we got this first line is going to be negative. This line is going to be, and this line is. So we've got a negative times a positive, which is ultimately a positive. And so we have this 0, and this is just a rough sketch. I don't know where exactly it's going to be, but it's positive, and what is it doing? It's coming meet the 0. Okay? What about in section B? What are we multiplying together? This is our x-axis. Same sort of procedure as last time. What are we multiplying together? So this line is, and this line is. So we have a negative times a positive times a positive, which ultimately gives us a negative. So this is going to go down, but what's going to happen? Why is it coming back up? It's got to meet that 0. And then, so this is for B. Let's look at C now. What's happening in section C? It's this little narrow piece right here. So this line is positive. This line is, and this line is. It's getting real messy. It's tangled over here, but all three of them are positive, which means, and so positive times positive times positive is a positive. We know how to do that. And so it's going to go up, but what's got to happen? Why is that? Because we got a 0 still. We got to come back to. And then now let's look at section D. So now we're looking to the right of this dotted line. We have a positive and a negative. So this is going to come back down like that. And I will trace over it with a different color so you can see. This is the. It's a rough sketch. But that's basically what it's going to look like. And if we pull up, this would be a good opportunity to check with our graphing technology. So our original expression was x plus 2 times negative 3x plus 2 times 2x plus 1. And it wasn't a perfect sketch, but look at where the zeros are. They're right where we expected them. And look at the shape of the graph. It's a little bit steeper than mine was. I didn't go, I sort of went, short little humps there, but so does the sketching process make sense? Let's break it down. What are the steps? What's the first thing we got to do? Find the zeros, but what's the purpose of finding those zeros? Zeros are roots. Yeah, we set the function equal to 0, but what do we do with those roots? We plot the roots, and then what do we do with them? Okay, so step 1 would be to graph the lines, the component lines.
You can just call them factors, because sometimes they will
Sometimes
be
they won't be
quadratic
lines, sometimes they'll be
factors.
quadratic.
Yeah.
Where do you want us to write?
I would probably write it on the page you've been working on. I would probably use this page
If
to
you're
help you
having trouble
study.
sketching, this is how you sketch. This is it. This is the thing to remember. So you graph the factors. And when you graph the factors, you'll already see what the roots are, but take note of where those roots are. And then once you have those roots, partition, is that a word that we know? Divide.
I would just draw vertical lines through your roots.
Yeah.
They might, but not. We just haven't used that in the context of this class.
So you're breaking up the graph into sections based on those roots. And then let's mark this circle down. Between roots.
Going down.
We'll restart it. It's gonna be nice and pretty for y'all, I promise. Between the roots, multiply to notice the, I don't know, how would you describe that?
The dilated function. So between the roots, multiply the types of y values, right? So whether the y value is what or what? Positive or negative, right? So you're multiplying the types of y values to figure out if a dilated function is positive or negative, because that's a lot of words.
Let's figure out if it's positive.
Okay.
That's the time.
Teachers and students, please pardon this quick interruption. Anyone who has made a composite 30 on their ACT, please send either Ms. Morrow or Ms. Woodruff a screenshot of your score. I realize that the April 11th seating
Hey, guys.
would not provide your
Please note,
scores yet.
we have to have an understanding check on sketching these factors or these dilated functions. So you need to study especially lessons 2 and 4 tonight. We do not have time to sit there and just stare at blank paper for a long time, so you need to come in ready to sketch. We are also going to have a little bit of this multiplying factors on this understanding check. It's tomorrow. We have to do this because we have to test on Monday with this whole unit. So we are doing understanding check tomorrow, wrapping up what we're doing here, and then move into a couple of other small details after that. Have a good rest of your day.